will happen. Right, as an example, 2. Let's say that we have not A or not B, and we say that this is valid for C. Meaning here that if we assume that premise 1 and premise 2 here are true, right, it should be the case that C has to be true, right? And so we could put this into a truth table, and if you use PLBot, that's how it works. It generates a truth table for it. But humans can't really do that very well very quickly, and so instead we have the natural deduction rules, which are over here. So last time we learned about the 8 replacement rules. Let me see my comment bar. So like, for example, modus ponens, if we remember that if we get the left side of an if-then statement, which is the arrow, then we get the right side. So we can use these rules, which use multiple lines, except for my favorite rule, which is add rule. Or we can also now use the 10 replacement rules. And the way that the 10 replacement rules work is that you should view these as like equalities in math. A statement of this form is going to be equal to a statement of this form. So whenever you see one of these two, you can replace them for the other one. Another very simple one is, for example, or statements, right? If it's P or Q, that's going to be the same as Q or P, right? There's no difference between those two. And so through the rule of commutation, you're allowed to switch them around. But there's also some cool rules here, mainly for this problem, which we'll do now, is De Morgan's. So De Morgan's lets me take a statement like this. Let's see, this guy. And then turn it into a statement that looks like this. So we see in our problem that this statement here, right, is this guy on the left. It's that guy on the left, sorry. And so since we see that, we can turn him into this in line 3 will be here. And so we could say validly or correctly that A or not B is true. If this isn't true, if this is true, then C is true. We're operating with De Morgan's on this. So we say, DM of line 1. Notice it only takes one line. We're De Morgan'sing this. And now with the modus ponens rule here, we see that this is the left side of an if-then statement, and then this is also the left side. So we get the right side. Right. So we could write C here by modus ponens of 2 and 3. And so we could prove that this argument is valid using these new rules. And that's a lot quicker than doing the proof table. Does anybody have any questions about what the usage of replacement rules or what's going on here?
Nope.
All good for you, Dantist?
All good for me.
All good for you. Okay. So the other important replacement rule, De Morgan's is used most of the time. It's a very common used rule. You'll use it a lot if you do a lot of these problems. The other rule that's very important for replacement rules is really the material.
Are these like?
Yeah.
Are these like the woofs or WWF thing or something?
IFF. So this is the triple bar. So it's this guy, which is equal to IFF, if and only if.
No, it's not what I meant. I think there's like something that's called WWF. It's a woof or something.
WWF.
Never mind.
Are you and Bulk Bogan hanging out with the WWF reference?
No. Never mind.
Yeah. But like the reason why this rule is important is it's the only rule on our magical rule sheet. I think I have an image of it. I'll put it in the chat. Let me see. Arthuria. logic rules.png. Yeah, so you can see them. It's the only rule that applies to the if and only if statement. So in a lot of problems, you'll get stuff like, I guess, let's do like A, or let's do like A and B, if and only if C or D. 2 might be something like, yeah, this will be interesting. Let me see if I make it right. Right. Prove that C or D is true. Okay. Now, this problem. It's pretty nice. So before we didn't have any rule to deal with statements like this. So what material equivalence does, and this is actually why it's the double arrow like this. That's why it's the double arrow, is because of this rule. So the material equivalence rule states, right? If we look here, right, that if I have a if and only if statement, I can turn it into an and statement where I have a conditional going both ways, right? In this case, if I have P, I get Q through modus ponens. In this case, if I have Q, I get P, right? So it's saying if I have one of the two, then I get the other one, which if we remember back up to our truth tables, right? That's exactly what the if and only if statement is, right? Where if both are true, right, then if both are the same rather, then the statement is true. So modus tollens also works. But that's what that rule is based off of. Okay. So we're here. So we can apply this material equivalence rule to line 1. Again, you're basically just looking at the form of the statement, saying this is the left side, this is my P, this is the right side, this is my Q, and you're just copying those into, oh God, wrong thing. You're just copying those into the material equivalence rule. So in this case, it's going to look a little bit funny and shocking at the start. Hi, Argo.
Hi.
So this will look a little bit funny at the start, but it'll make sense. And B. Then, if that's true, C or D. Right? And then it also goes the other way. So this would be C or D is true. If then A and B are true. Okay. 4. And we got this through our new rule, the material equivalence or equiv rule. Very important rule. Equiv of line 1. Okay. So this is a big scary statement, right? But when we break it down and we look at, hey, this is the right side and then this is the left side, right? And we know it's an and statement, it becomes a lot less scary. All that this becomes with our, if we remember our simp rule, when we have an and statement, or the conjunction, so it should be here. With our simp rule, right, we know that whenever we have an and statement like this, we just automatically get both the left and right side. So we can see what that will look like. And it'll be a lot.
Wait,
Yeah.
1 second. Is it actually called simp?
It's called simp, yeah.
That's hilarious.
Yeah, I get a kick out of it. But don't be a simp and always simp your and statements. It makes your life a lot easier. You know, you get free internet points or something. Whatever the new kids' words are for simp or whatever. I will say, if a rule was named cuck, I would not use it. Okay, so this comes from simp of line 1 and sorry, line 3, and then we also get the other side. A and B. Right? Again, remembering that this is an arrow going both ways, right? And so it makes sense that we have the arrow going from A and B to C or D. And we also have the arrow of C or D going to A and B. Again, for if and only if to be true, if one of them is true, then the other one has to be true, right? So we get this, we get these two statements. Does anybody watching see what rule we should apply to be able to get our conclusion from here? It's a two-step process.
Oof, I actually don't know.
So, applying our trick right, let's look to the conclusion. Right? The conclusion is this, and the conclusion is here. Right? So, if we had this guy, right, then we could modus ponens. So how do I get this guy? Well, we haven't used line 2 yet. So it might be a clue to use something in line 2. What is not A?
Isn't that A?
It's double negation.
Wait, can I not talk? Sorry.
Oh, you had a question?
Oh, wait, are we allowed to talk in here?
Yeah.
Okay. Yeah, it's A. Double negation.
So double negation lets us take anything that looks like this with two knots, and it lets them take it away. So I can write, remembering logic is stupid, and you have to do it one step at a time. Do this. dn of 2. Then let's do it to b. It should be double negation of 6. Oh no. No. Okay. And so now, right, we see this and we see this. Right. And that's going to be modus ponens. So then in line 8, we can write C or D with our favorite rule, right? Modus ponens. Everyone's favorite rule for some reason. And what lines were these? 4 and 7. Yeah. So that would be that guy. Questions about this?
Wait a second. 4 and 7?
Yep. 4 and 7.
Shouldn't it? Wait, don't you need 5 as well?
Why do I need 5? I got there without it. So to do any now,
Oh, that's true. Yeah,
I
right.
can't do anything with line 5, unfortunately, right? Because this is the same. I can't modus tollens it.
No, you're right. You're right.
So now when I have C or D here, right, no one prevents me from modus ponensing 5 later. Nothing prevents me from doing that, but I have the problem here, so you just don't need to do that. Stop doing that. Right? Any other questions about this?
It's a pretty slow method. Kidding.
You think slow? Well, you can do these in your head.
Yeah, I know. I'm just joking.
That's the advantage. So there's another way to do it. So if we bracket this stuff off, leave this guy alone, and let's do a different way. So this is testing like how conceptually the replacement rules work. I can apply De Morgan's to this puppy. Right? I can do this. So De Morgan's rule says whenever I have something negated, right, with an or sign, I can bring it outside and I change the sign. Right? So something is being negated here, namely not B is being negated, right? And namely not A is being negated. So I can De Morgan's it. And that would look like this. Be not. So I take a not out, right? And I change the and to an or. And I would change an or to an and, as I'm about to do. So then this would be De Morgan's of 2. 7. I can De Morgan's this thing, actually. Why not? So I just take out a not. So now there's 2 nots. And I write A and B. De Morgan's of 6. Then an 8. I now apply my double negation rule. This is a longer way. I get A and B through my double negation. 7. And now this other stuff runs. Instead of being in 7, we're 1 line longer, it looks like. It'll be line 8. So you see that there are multiple roads that lead to Rome, right? It does seem, however, that there has to be a double negation somewhere, right? And then there has to be this modus ponens. It seems like that these are the 2 necessary steps to solve this, as well as then, originally breaking up the if and only if statement, the biconditional. Questions about that usage? Everybody on board?
I'm on board.
Arco, any questions?
Not right now.
We're all good? Okay. Okay, other rule that's important is so some rules are based on each other. We can prove that transposition is true if you grant me these over here. If you grant me what is it? Where is it? Where's my conditional changer? Material implication. With material implication. These 2 rules are related. So, okay, let's prove it. So, the proof, and this is proving like what could be considered a tautological statement. So, it's only one premise. It only takes one premise. So, I want to prove that if P is true, then Q is true. And I tell you that if this if then is true, basic if then statement, that if not Q is true, then not P is true. Okay. Anybody disagree with this? I'm just curious.
It seems It seems like that's wrong.
This is modus tollens, actually. You think about it, right?
Yeah, I guess I need to freshen up on that.
So think about it, right? Like, look at modus tollens. Modus tollens says that if I have the negation of the right side, I get the negation of the left side, right? So this is saying, hey, if I have the negation of the right side, I get the negation of the left side. We're essentially proving modus tollens here with different rules.
Okay.
Which is fun, right? Okay. So material implication rule is also very useful. It turns an or statement to an if then statement. If people want to do a truth table for it, maybe we could do one. Okay. So if we apply material implication, right, it just does this, right? Exactly as the rule says. Right? This is impel. I call it CE usually, is what I prefer to call it, conditional exchange. Because we exchange the conditional. Now, with com rule, which I mentioned earlier, we get to flop the order of them. Okay. Why are you doing that? Necessary move. Because unfortunately, order matters for conditionals, right? That's the whole point of conditionals. This is the only one that matters. Where the order matters, which is what makes them different. Okay. Now, I'm going to use the other usage of double negation. I'm going to add 2 knots to the queue. And you're like, why? Why am I adding 2 knots to the queue? Somebody? So look at the material implication rule. Right, this turns into if not Q, then not P through impel again. Right? Because impel says, hey, if you have a negation on the left side, this guy, right? This guy is negating this. I want to argue. Right? And so I drop this not, and then I change the or to an if then, and I write impel for, and I win. Right? Sneaky proof.
That is very sneaky.
Yep.
But you see, you can have fun with this. We can't prove all the rules in this way. In fact, some people don't believe we should use replacement rules and they're anti-fun because this makes the process a lot faster. But you could prove De Morgan's using conditional proof and indirect proof, and you can prove the other things with that. But I just like having these rules here so I don't have to go through a 6-step gyration just to get this, you know? Oh, I have to prove that com is true by yes, like that. That's how the replacement rules work. If you want to, we can try solving more problems, but all the rules basically just work this way. You can basically, as long as you fit the form, for example, as long as you fit this form in some manner, you can write what it's equal to. And that's how those work. And then you just be on the lookout to see if, usually, the way that replacement rules work strategically, this is an exception. But if you remember the last problem, usually the way that you use the replacement rules is so that you can do a modus tollens. So you can do a disjunctive syllogism. You can do maybe a modus ponens, right? These are the reasons why you're doing these replacement rules, is to get that negated right side, for example. I can hide a modus tollens in a problem, very easily. And we can see that. So if we like a puzzle might be, if P is true, then Q is true. Very simple, right? Now I'm going to put some junk here. Let's do like A or B. And then if that's true, then if A or G is true, then Yeah, how do I want to do it? Okay. Yeah. Then not Q or P. Okay. And I'm telling you that Q is true. There's a modus tollens here. Oh, I have to give you one more thing. I give you one more thing to make this puppy work. I give you A.
And what's our goal in this task?
Goal is Q. Sorry, not Q. Rather, not Q. Actually, no. Not P. Get not P. And I'm going to take this guy out. Yeah, sorry. This is easier. Proves the point more easily. Yeah, so this you actually don't need replacement rules for, but we can use them to affect if we wanted to. I mean, does anybody have an idea how we would solve this problem?
Well,
So I have A. I need not P.
I have this feeling of starting inside the parentheses.
Okay. So here, you want to do this guy?
Yeah, just because that's where Q is, and P and Q are related. And if
Yeah.
I'm trying to get not P,
Yeah, so you can do several things to this guy. All right, you can do several things. We could write him like this with the what we just learned with our impel rule, right? Why not?
and then can we simp inside of that because of the and?
We cannot. There is no and, it's an or.
Oh, sorry.
We can't simp, right? Because he's bound. He's bound on the right side of this guy. We could turn it to this if we want to go crazy, and I'm fine with this. This reaches a valid solution. We write this. So now we've created a big or statement. This is fun. All right, this guy is now a big or statement. Well, when you have or statements, right, we use disjunctive syllogism on them to get rid of stuff. All right? We use disjunctive syllogism here somehow. And I can use my favorite rule, add, to get to a disjunctive syllogism. So I see that A and A or B look similar. And I know that if I know A is true, then I will know for sure that A or B is true. Why? Because the or statement only needs one of the two sides to work, right? So this statement is true no matter what B is, because I know A is true. So I either have A or something that doesn't exist. It's still true. Now, if I throw a double negation, like we learned in the previous lecture, around around this, Bn of 6. Now we see that this guy, right, he is the negation of this guy. And so we can apply disjunctive syllogism. which nets this puppy. Five and 7. 9. But notice what we did, right? We used the replacement rules. We used the double negation replacement rule to build this guy, which we then used one of our implication rules with. And that's usually the pattern that I've seen, is you use the replacement rules to get somewhere else. So to do the problems quickly and in your head, you kind of have to memorize through usage these equivalences, right? Because you can see statements as the same thing as what they're equal to with the replacement rules, and it makes it quicker for you to find out where you can actually get work done with the implication rules. The implication rules do actual work. The replacement rules just make things look different. So when we're here, right, we no longer need these parentheses, but we can, funnily enough, apply the same trick. We're going to use the same trick twice. And the same trick is we're going to write ARG with add, because my favorite rule, had to make it multiple times. Add of 3 again, 10, the exact same trick, not A or G, or right here. Sorry, I got a little bit ahead. Double negation of 9. Then 11 will be not Q, right? Through disjunctive syllogism again. Disjunctive syllogism of 8 and 10. And then 12, we get our not P through the modus tollens of 11, 1. So remember I said that you can hide a modus tollens in something very easily. So when I made up this problem, right, my thought was I'll give you what you need to get rid of this guy. And then inside of that, I'll also give what you need to get rid of this guy. So then you modus tollens 1 with your not Q that you eventually get out of it. Right? The way that I built this problem was I looked at the problem as really being like this. This is what the problem really was. But I had to use implication rules to make this garbage look like that. Right? Another way to look at this problem, which would also be a correct way of looking at it, would be A, if A is true, then A is true, then if A is true, then not Q is true. That's another way of looking at this problem. Questions? Does that make sense?
Yes.
You didn't have to do this impel though, I don't think. I think you can just start adding and then do modus ponens it all the way down. But I like this route. I like that it turned out to be an entire OR statement. That was fun. Oh, another famous case of stuff that is stupid that nobody likes in logic who does it. So let's say I have some Q and B here, right? And then I have Q if and only if B. And then 2, I gave you Q and B. Sorry, make this something else, sorry. Q and P. Okay. Similar style problem. I want B out of it. B is the MacGuffin that we're searching for. So in 3, right? Now, you could do material equivalence in this guy if you wanted to. You could do that. And it will look really stupid and it would be very long and will hurt your brain. So I advocate for not doing this. And if B is true, then Q is true. And then we have another set of parentheses. Are we good? Yeah, we're good. Right? I would recommend, oh, B is true, then Q is true. I'd recommend not doing this. The reason why you don't want to do this is because this is messy and looks annoying. And it can especially get lost if, for example, I had it like this, right? Something even more stupid, like this, right? Now here, we have to add another and D and a parenthesis. And see, now it's starting to look really ridiculous. So if you do this stuff inside of parentheses, you're going to get something that looks like this. So I caution against doing that. Instead, I would look around first to try to free this garbage from this garbage. Because that's the problem with if-then statements, right? Is this garbage, it constrains this right side to be bound to this guy. Where with other operators, they're a little bit more free in a sense. So here instead, I would prefer to do this instead for this, which is much simpler and easier for brain to understand, which would be an MP of 1 and 2 instead. Now I want to get them all the way out of any entailment to anything else whatsoever. And now I would do my material equivalence rule, which would be this. And then Q, of course, with parentheses, gotta make it look good. And then here, 6. We only need if Q, then B. It's the only thing we need. 7, we free up the Q because we have to. And then 9, B is true. So if someone wants to fill in what steps I did, that would be a good exercise. So what rule did I apply in line 4?
Is that a simp?
Correct. Absolutely. It's a simp of line 3. This rule is what?
Is that the addition?
No, it's our equiv rule
Oh, fuck.
from 4. Equiv of 4. And then this is what? This is our friend simp, right? Q is what? Where am I getting Q from? Where in the world is this coming from? Okay, let's cross out the possibilities. Not this guy. This guy already did something to. Can't be this guy. This guy can't. If this was Q, I could have. Okay. I can get Q out of this guy with simp. It's an and statement. And then B is the crowd favorite rule, modus ponens of 6 and 7. I like it when it looks like this. Personal preference. Questions on that? But again, if you wanted to do your equiv inside of this guy, you can. You'll just write more. Because you have to carry this statement along with this guy once and then and D once. When here you only have to do it one time. You know, I saved you two big writing steps by doing it this way. Okay. Any more questions on this? I mean, if you got your implication rules down, then your replacement rules are just more of the same basically, except you're more free to use them. Right? You can use these inside of parentheses. So that's the only real substantive difference between the two. Now, I guess next time, if it has these, we could do identity, but it's kind of boring. I wonder if it had the indirect or direct proof. Let's see. Oh, he doesn't have it in rule sheet. But what we'll be doing next time is called indirect proof, which is my favorite proof method and how I beat the bot. And then we'll also be discussing conditional proof.
Nice.
So an indirect proof, just for your information, is assume that the conclusion is false, ... and then prove to me that some not X and X is true, some contradiction. And then your exit from this is going to be not C, which is then C. Conditional proof works much the same way, except you just assume something, you assume A, you do some derivations, and then we come out of it with if A is true, then X is true, where your last line here is X. So that's what we'll be learning next time.
Excellent.
All right, thank you all for coming.
Yeah, thank you, CoolDoG. I need
Oh.
to practice a lot of this stuff from the last lesson because I think I was struggling with some of the basics from last time in this one.
It's just practice.